An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Consider a soccer ball on a field. The ball will not move unless a player kicks it, applying a force. Once kicked, it will continue to move in the direction it was kicked until friction between the ball and the grass and air resistance gradually slow it down and stop it. Light is a form of electromagnetic radiation that is visible to the human eye. It is a small part of the electromagnetic spectrum and radiation given off by stars like the sun. Light behaves both as a wave and a particle, a characteristic called wave-particle duality. It has properties of waves, such as wavelength and frequency, and can also be thought of as a stream of photons, which are massless particles. 9 experiments about light in history. 1. Isaac Newton, Prism Experiment, 1672. Newton passed sunlight through a prism, which split the light into a rainbow of colors. This showed that white light is a combination of different colors. Imagine using a kaleidoscope that separates the colors you see in a beam of sunlight into individual colors like a rainbow. Before Newton, it was thought that colors originated from a mixture of light and darkness. Newton's experiment challenged this. He showed that white light is a blend of various colors, which are visible when light is passed through a prism. This was like showing that a white sheet of paper is actually made up of different colored threads when looked at more closely. He argued that objects don't have color themselves. They simply reflect certain wavelengths that appear as colors to our eyes. This was a major shift in understanding light and color. It led to the field of spectroscopy, which studies how matter interacts with electromagnetic radiation. Newton's work established that light has a spectrum and that color is a property of light itself, not something produced by the interaction of light and darkness. It also hinted at the wave nature of light, as different colors bend by different amounts due to their wavelengths. However, Newton himself believed in the particle theory of light, showing how one experiment can lead to diverse interpretations and advancements in science. 2. Albert A. Michelson, Speed of Light, 1879. Michelson used a rotating mirror setup to measure the speed of light with unprecedented accuracy. Imagine timing a sprinter running a known distance back and forth, using a stopwatch that starts and stops as a mirror reflects light to a sensor. Michelson's experiment was like using a highly precise stopwatch to measure the time it takes for a runner, light, to travel to a distant mirror and back. His rotating mirror technique was ingenious. It allowed for the measurement of the time delay of light reflected between mirrors. This was crucial because knowing the speed of light with accuracy is fundamental to physics. It's like knowing the exact speed of a car in traffic laws. It sets the rules for how we understand movement and interactions. Michelson's work influenced many areas of physics. It showed that light travels at a finite, measurable speed, and this speed is constant in a vacuum, an idea crucial for Einstein's theory of relativity. His work essentially laid the groundwork for modern physics by providing a constant that is used in various fundamental calculations. 3. Thomas Young, Double-Slit Experiment, 1801. Young shone light through 2 parallel slits, and the light created an interference pattern, demonstrating light's wave nature. Imagine dropping 2 stones at the same time in a still pond. The ripples created by the stones overlap and create patterns, similar to the interference pattern in Young's experiment. Young's experiment was like watching the water waves from 2 stones interact in a pond. When light was shown through 2 slits, it created a pattern of bright and dark bands on a screen, not unlike the overlapping ripples creating highs and lows in the water. This showed that light behaves like waves, capable of interference. Before this experiment, light was thought to consist only of particles. Young's work was revolutionary as it directly challenged this view. The interference pattern was a clear sign of wave behavior, something particles alone couldn't produce. This experiment was the first strong evidence for the wave theory of light. It also paved the way for understanding that light has properties of both waves and particles. This concept, known as wave-particle duality, is fundamental in quantum mechanics. Young's work helped explain phenomena like diffraction and the color spectrum. It was a key step in understanding the nature of light, influencing how we develop microscopes and even how we understand the vision in biology. 4. James Clerk Maxwell, Electromagnetic Theory of Light, 1865. Maxwell mathematically showed that light is an electromagnetic wave, predicting its properties based on electric and magnetic fields. Think of a sea wave, light, being described perfectly by a set of equations, Maxwell's equations, predicting how it will behave under different conditions. Maxwell's work was like discovering the rulebook for how a specific kind of wave, light, behaves in the ocean of electromagnetic fields. He didn't do a physical experiment. Instead, he used mathematics to describe how electric and magnetic fields propagate and interact. This was groundbreaking because it unified electricity, magnetism, and optics into a single theory. Maxwell's equations were like finding a universal language that could describe a vast range of phenomena. They predicted that light is an electromagnetic wave, a concept that was revolutionary at the time. This theory provided the foundation for understanding how radio waves, microwaves, X-rays, and even gamma rays work, as they are all part of the electromagnetic spectrum. It's akin to discovering that different musical instruments, despite their differences, all produce sound waves that can be understood through a common principle. Maxwell's work paved the way for the technological revolution of the 20th century, leading to inventions like radio, television, and radar. It fundamentally changed our understanding of light, showing it as part of a broader spectrum of electromagnetic radiation. 5. Heinrich Hertz, discovery of radio waves, 1887. Hertz created and detected radio waves in the laboratory, confirming Maxwell's predictions. Imagine creating ripples in a large water tank and then using a detector on the other side to capture and measure these ripples. Hertz's experiment was like proving the existence of a previously theoretical animal by not only spotting it but also capturing clear pictures of it. Hertz used a spark gap transmitter, a simple device that created sparks that emitted radio waves. Then, with a receiver, he detected these waves, confirming they behaved as Maxwell's equations predicted. This was groundbreaking because it was the first time electromagnetic waves were observed directly. His work led to the development of wireless communication. It was a pivotal moment in the history of technology, akin to the discovery of fire in terms of its impact on human civilization. Hertz's experiment showed that not only does light have companions, radio waves, in the electromagnetic spectrum, but these waves could be harnessed for communication, transforming society. 6. Albert Einstein, photoelectric effect, 1905. Einstein explained the photoelectric effect, where light ejects electrons from a material. He proposed that light consists of particles, photons, and the energy of these photons is related to the light's frequency. Imagine a pool table where the cue ball, photon, hits the other balls, electrons. If the cue ball is hit slowly, low-frequency light, it won't displace the other balls. But if hit fast enough, high-frequency light, it can knock them out of their place. Einstein's explanation was like solving a mystery where traditional understanding couldn't explain why only high-frequency light could eject electrons. Before this, light was mainly thought to behave as a wave. But the photoelectric effect showed that light also behaves like a particle. This was akin to discovering that water, which is usually a liquid, can also act like ice under certain conditions. Einstein's work showed that light's energy is quantized, coming in packets, photons. The energy of these packets depends on the light's frequency, similar to how the force of the cue ball depends on how hard it's hit. This was a crucial step in the development of quantum mechanics, a field that explains how the microscopic world works. It was as if Einstein found a new rule in the game of physics that only applied at a small scale. His work on the photoelectric effect laid the groundwork for modern electronics, including technologies like solar panels and digital cameras. Einstein's contribution significantly advanced our understanding of light, showing that it has dual characteristics, wave-like and particle-like. 7. Arthur Compton, Compton scattering, 1923. Compton demonstrated that X-rays, a form of light, scatter off electrons and change wavelength in the process, showing light's particle-like properties. Compton's experiment was groundbreaking because it showed a clear interaction between light, as photons, and matter, electrons. Before this, light interacting with matter was primarily understood in terms of waves. Compton showed that X-rays, when they collide with electrons, behave like particles being scattered. The change in the X-ray's wavelength was direct evidence of this particle behavior. Compton scattering was a significant piece of evidence for the dual nature of light. It supported the idea of photons carrying momentum, a trait typical of particles. It was as if Compton discovered a new way in which the microscopic components of the universe communicate, broadening our understanding of the fundamental interactions in nature. His work further cemented the concept of wave-particle duality in light, illustrating that light doesn't conform to a single classical description, either wave or particle, but rather exhibits properties of both depending on how it's observed. 8. Leon Foucault, speed of light in water, 1850. Foucault measured the speed of light in water, and found it to be slower than in air, contradicting the Newtonian prediction that light would travel faster in denser media. Think of a car, light, traveling on different terrains, media. It moves slower on a rough road, water, compared to a smooth highway, air. The slowing down of light in denser media is a characteristic of wave behavior, not particles. It's similar to how sound travels at different speeds through air and water. It also led to a better understanding of refraction, the bending of light when it passes from one medium to another. Understanding how light behaves in different media is fundamental in designing systems where light needs to be manipulated. 9. Romer, speed of light from astronomical observations, 1676. Romer estimated the speed of light by observing the timing of eclipses of Jupiter's moons, noticing delays caused by the varying distance between Earth and Jupiter. Romer's approach was akin to calculating the speed of a car by measuring the time it takes to travel between cities at different distances. He observed the moons of Jupiter and noticed that the time between their eclipses varied depending on Earth's position relative to Jupiter. This was a clever way to use astronomical events as a cosmic stopwatch. Before Romer, the speed of light was often considered infinite, as it seemed to travel instantaneously. Romer's observations challenged this notion. He noticed that when Earth was moving away from Jupiter, the eclipses appeared later than expected, and when Earth was moving towards Jupiter, they appeared earlier. This delay was a clue that light took time to travel. It was like measuring the speed of sound by timing the delay between seeing lightning and hearing thunder, but on a much grander scale. Romer's method wasn't exact by today's standards, but it was incredibly innovative for his time. His method of using astronomical observations opened new avenues for scientific inquiry, demonstrating that the universe itself could be used as a laboratory for understanding the laws of physics. If you found this exploration as intriguing as I did, don't forget to give it a thumbs up and hit that subscribe button below. Make sure to ring the notification bell so you never miss out on our upcoming scientific explorations.